In this video we will discuss the engineering change order, or eco flow, in Vivado. We will talk about what it is and why it can be useful before looking at a practical example of how it works. In IC development, an engineering change order is a modification of a design that takes place after the standard flow for design entry, which is usually done through HDL code processed by logical and physical synthesis tools. These changes are generally small compared to the scale of the original design, and can be introduced in the gate-level netlist, or even by modifying a few of the metal layers after the masks for the production of the IC have been finished. In FPGA designs, engineering change orders can be made on the placed and routed netlist. This allows us to make modifications to our design without having to rerun synthesis and implementation, both of which can be quite time-consuming. Engineering change orders also make it possible to modify the design without having access to the original source files, or to try small changes directly on the hardware before committing them to the RTL code. Vivado supports an eco flow that enables us to make changes to a placed and routed design checkpoint. With the eco flow, we can alter the connection of individual nets, add or delete cells, and replace debug probes. The starting point for the eco flow is a placed and routed design checkpoint, which means we start by running synthesis and implementation for our original design. If we are in project mode, all design checkpoints are generated automatically. In non-project mode, we must create them explicitly. Once we have our placed and routed design checkpoint, we can open it in Vivado. After it loads, we select the eco layout from the main menu. The two most relevant panes in the eco layout are the eco navigator and the scratchpad. The eco navigator provides access to the commands and analysis tools relevant for the eco flow. The scratchpad keeps track of all the elements that we have edited in the eco flow, and indicates whether each one has been connected, placed, and routed. The first step in our eco flow will be to change the inputs of a multiplier cell, so that its functionality changes from multiplying the input value by itself, to multiplying the input value by 2. We start by locating the multiplier in the schematic. Once we have found it, we select the input 2 and then click the Disconnect Net button in the Eco Navigator. We can then see that the net is disconnected from the selected input, which is now floating. The scratchpad shows that the nets that we have just disconnected are neither connected, nor placed and routed, which is what we would expect. When we select the pins we just disconnected and click on Connect Net in the Eco Navigator, a dialog opens where we can choose which net we would like to change the connection to. Because we want to multiply by 2, we set bits 0, 2 and 3 to constant 0, and bit 1 to constant 1. Going back to the schematic, we can see that input 2 of the multiplier cell reflects the changes we just made. We have changed the logic of our design without changing our RTL, and therefore without having to rerun synthesis and implementation. In addition to modifying the cells that are already in the design, the eco flow allows us to add new cells. We will add a new lookup table, define its equation, and use its output to drive the input of a register. In the Eco Navigator we click Create Cell, which opens the Create Cell dialog box. Here we can enter a cell name, search for, and select the cell type, and enter any additional information required. In the case of a lookup table, we need to specify the equation that it will implement. Once we have created a cell, we need to connect it to other cells in our design. One way to do this is to select a net from the schematic, then hold down the Control key while selecting the corresponding input of the lookup table from the scratchpad, and then click on Connect Net in the Eco Navigator. We repeat this process for all the inputs and the output of our lookup table. The eco flow in Vivado includes a dedicated process for changing the inputs to an existing integrated logic analyzer core. This can be very useful when we are debugging a design on the hardware, because it allows us to capture data from our logic much more quickly than if we needed to rerun synthesis and implementation every time we wanted to probe a different set of signals. To swap debug probes, we click the Replace Debug Probes button in the Eco Navigator. In the Replace Debug Probes window we see a list of the integrated logic analyzer cores present in our design. When we click the Edit Probes button to the right of the name of the probe that we want to replace, the Choose Nets dialog box opens. Here we can search for the net that we would like to probe and add it to the selected box on the right side. After we have completed the eco flow, we need to rerun place, route, and bitstream generation. However, before we do that, we want to make sure that the changes that we made did not introduce any design rule violations. We do this by clicking the Check Eco button in the Eco Navigator. It is expected to get critical warnings regarding unplaced and unrouted nets and pins that we have changed in the eco flow. They will be solved when we run place and route. However, we should make sure that all other elements in the design remain unaffected. After running design rule checking, we can start place, route, and bitstream generation. If we made changes to the debug probes, we can generate an updated LTX file to use in the hardware manager. All these steps can be started from the Eco Navigator. The Eco Flow allows us to make minor changes to the design directly on the placed and routed checkpoint, without updating our RTL files or rerunning synthesis and implementation. This can be very useful for iterating quickly when doing hardware tests or debugging a design. We can use the Eco Flow to change net connections, add and remove cells from our design, and swap debugging probes. After making changes in the Eco Flow, we can run DRC to make sure that we haven't done any illegal modifications. We are then ready to run placing, routing, bitstream generation, and to create an updated LTX file for debugging in the hardware manager.